So hello once again. Today I'll be going through a quick crash course on reaction kinetics. So first, what is reaction kinetics? Reaction kinetics is basically the study of the speed at which a reaction occurs. So the keyword here is speed at which a reaction occurs. So we'll take a look at this reaction over here, where A moles of this species A reacts with B moles of this species B to form C moles of this product C and D moles of this product D. So first we need to define what do I mean by speed of the reaction. In other words, what do I mean by the rate of a reaction? So for example, to define the speed of a car, we would say that speed is the distance travelled with respect to time. However, in this case, we can define it based on any one of these quantities: the concentration of A with respect to time, the change in concentration of B with respect to time, the change in concentration of C with respect to time, and the change in concentration of D with respect to time, which are basically these derivatives over here. However, we need a unified definition of rate. That is, we can say what the rate of the reaction is without it differing whether we define it based on A, B, C or D. And so we divide these derivatives by the stoichiometric coefficient of the respective species. And we add a negative sign in front of the rate of change of the reactants. Why? Because the rate of change of the reactants is negative, but rate is a positive value. Okay? So there are a few types of reaction rate, more specifically 3 types. So the first type is the instantaneous rate. So we know that rate is defined based on the derivative, right? The concentration of a certain species dt. So it then follows that you can plot a graph of the concentration of a species, say a product, against time, and then draw a tangent, and we can find the instantaneous rate at that point in time t. And we can define initial rate as the instantaneous rate at t equals to 0. That means we draw a tangent at t equals to 0, find the gradient of the tangent, and we get the instantaneous rate at t equals to 0, and we call this the initial rate. So, however, the problem with these methods is that you need to have a graph of concentration against time. But sometimes you don't always have the luxury of such a graph. The average rate is an approximation for the instantaneous rate, where it's basically the difference between two concentrations value measured at two different times divided by the time elapsed between the two different timings. So I can also say that average rate is concentration, final concentration, minus the initial concentration divided by the time elapsed, which is the final time minus the initial time point. So that is the average rate. So let us take a look at experimental methods by which we can measure rate of a certain reaction. So the first method is the continuous method. So it tracks the concentration of the reactant or the concentration of the product over time. So we need to take these values of concentration of reactant or concentration of product over time and plot the graph of concentration against time, as what we have done early, as what I've shown you earlier. The graph of concentration over time will look something like this, and we can draw a tangent to the curve at any point in time to find the instantaneous rate at that point of time. The second method is the clock method, which measures the time taken for a prominent visual change. So the key observation here is a prominent visual change to occur, which corresponds to a certain fixed change in the concentration of the product, or a fixed decrease in the concentration of the reactant. So this fixed change in concentration of the reactant, when divided by the time that's elapsed, will yield the average rate at t equals to 0, which is an approximation for initial rate. So as we'll see later, we are normally quite interested in how the rate of the reaction is dependent on the concentration of the reactants. So what we can do is we can vary the initial concentration of the reactants we are using and then see how the rate of equation changes by deriving rate based on the time taken for the prominent visual change to occur. And often the total volume of the reaction mixture is kept constant, so that volume of the reagent is proportional to the concentration of the reagent in the reaction mixture. Okay, to fully understand what this means, you have to go through a few interesting examples of reaction rate, which I may cover in a future video. So let us take a look now at what reaction rate is dependent on. So we will learn in the H2 syllabus that reaction rate is dependent on temperature, the presence or absence of a catalyst, and the concentration of the reactants. So we can express how the rate depends on the concentration of the reactants via the rate equation. So this is different from the mathematical definition of rate, in that instead of defining what rate is, it tells us, having known what rate is defined as, how this rate depends on the concentration of the reactants A and B. So we say that rate equals to A, concentration of A, to the power of X, times concentration of B to the power of Y, multiplied by a proportionality constant K. So we say X is the order of reaction with respect to A, and Y is the order of reaction with respect to B. K, on the other hand, is dependent on temperature and activation energy. We know that increasing the temperature increases the rate of the reaction. So K increases as temperature increases. We also know that the lower the activation energy of a certain reaction, the faster the rate. And so as activation energy is decreased by the presence of a catalyst, the rate constant increases. So X and Y, which are the orders of the reaction with respect to the reactants A and B, have to be obtained from experiment. So let us take a look at a few types of reactions. The first is the first order reaction. First order reactions are reactions where its rate is directly proportional to the concentration of one reactant raised to the power of 1. So the rate equation will be something like this, as you can see over here. And one thing that is unique, special about a first order reaction is that when you plot the graph of that reactant against time, right, we observe that the reactant has a constant half-life. In other words, if say the rate of the equation is dependent on the concentration of A to the power of 1, then plotting a graph of concentration of A against time, we'll get a curve such that the time taken to go from say x to half x, and the time taken to go from say 0.8x to 0.4x, which are basically two separate half-lives, they will be equal in value. And this half-life can be mathematically proven to be equals to the constant ln 2 divided by the rate constant of the rate equation, which is basically a constant at a constant temperature and activation energy. However, if we change the temperature, we'll expect the half-life to change as well. So second order reactions can be expressed. There are two types actually of second order reactions. The first one is where rate is dependent on the concentration of one reactant raised to the power of 1 multiplied by the concentration of another reactant also raised to the power of 1. Alternatively, another reaction with a rate equation dependent on the concentration of one reactant raised to the power of 2 is also called a second order reaction. So zero order reactions are reactions where the rate is not dependent on the concentration of any reactant at all, and is termed as a constant at a constant temperature. So let us take a look at something interesting right now. pseudo-order reactions. Say for the certain reaction with a rate equation, rate equals to K times the concentration of A times the concentration of B. If the concentration of A is much larger than the concentration of B, the percentage change in the concentration of A is negligible for a given change in the concentration of B. So let us take a look at an example. So A reacts with B in a 1-to-1 ratio to form the products. It does not really matter what the products are. So let's say concentration of A equals to 1 mole per dm cube. Concentration of B equals to 0.01 mole per dm cube. So you certainly agree that concentration of A is much larger than concentration of B. So let's say that after some time, the change in concentration of B equals minus 0.005 mole per dm cube. So basically, half of the B has reacted away. Then what is the change in the concentration of A? It is the same. But don't you agree that while the percentage change in the concentration of B is 50%, the percentage change in the concentration of A is much smaller. In fact, it is just 0.5%. So we can say that through the course of this experiment, when the concentration of B decreased from 0.01 to 0.005, concentration of A remains approximately constant. So we can group the rate constant and the concentration of A, which is effectively a constant, together and say rate equals to K prime times the concentration of B. Right, where this new rate constant K prime equals to the original rate constant K times the concentration of A and the half-life of B. Now do you agree this is a first order expression? So I can say that the concentration of the rate is proportional to the concentration of B raised to the power of 1, and that the half-life of concentration of B, which the time taken for concentration of B to a half, right, will be equals to a constant, namely ln 2 over the new rate constant K prime, equals to ln 2 over K times the concentration of A. So it is a constant throughout the course of one experiment run, but yet somewhat it also isn't a constant, because if I have to change the concentration of A in a separate experiment run, then the half-life will also change. So this is a pitfall that many students fall into, thinking that for a pseudo first order reaction, right, the half-life is really independent of everything except temperature. But no, it is also dependent on the other reactant, which we assume to be roughly constant. Okay, and another case where we see a pseudo order reaction is if rate equals to K times A times B, but A is a catalyst. So the catalyst will be consumed and also regenerated such that it is not consumed overall in the reaction, and the concentration of the catalyst A remains approximately, in fact it does remain constant throughout the course of the reaction. So we can similarly group that concentration of A with the rate constant K to form a new rate constant K prime. Okay, now let us take a look at the microscopic basis of reaction kinetics. So let us go back to this reaction. A plus B gives you C plus D with a certain activation energy. So this activation energy affects reaction rate through the rate constant K, as I've mentioned previously. And the relationship, this is not really in the H2 syllabus, but it's useful to know, is represented by the Arrhenius Equation. So we can see from this mathematical expression that if activation energy decreases by the addition of a catalyst, K would increase. Am I right? Okay, just take some time to take a look at the mathematical expression, right? If activation energy decreases, the power of E becomes less negative, right? That means E will be larger, A is just a constant, and K will be larger. Okay, and conversely, if temperature was to decrease, say we put it in an ice bath, right, since the denominator of this fraction over here is decreased, E is to the power of a more negative value, which means this value will be smaller and K will decrease. That means the reaction will proceed at a slower rate. So to understand more intuitively why this is so, we have to take a look at the Maxwell-Boltzmann distribution curves. So the Maxwell-Boltzmann distribution curves gives the number of particles. So some schools say number, but a more accurate version will actually be the proportion of particles, the fraction of particles with a certain energy. And the x-axis is the kinetic energy. So if I were to say what is the proportion of particles with kinetic energy x, I just have to interpolate into the graph and say that this proportion, this f fraction of particles have kinetic energy x. So let us take a look. What happens if you introduce a catalyst? When you introduce a catalyst, what we observe is that the activation energy of the reaction decreases because now we are having an alternative pathway with a lower activation energy. So we realize that there's more particles with energy greater than the activation energy. Originally, the number of particles with energy greater than the activation energy is this, but now with the lower activation energy brought about by the catalyst, it is this. Right? So the more particles that is having energy more than the activation energy of the reaction, the more likelihood that two particles with sufficient energy can collide in a productive collision to form the products. And so let us take a look what happens when temperature increases, because we also know that increase in temperature increases the reaction rate. So when temperature increases, the Maxwell-Boltzmann curve shifts down and more towards the right, such that the proportion of particles with energy greater than the activation energy also increases from this number to this number. So what we observe is that there are more particles with energy greater than the activation energy. More likely there will be two particles with sufficient energy coming together in an effective collision to form the products, thus a faster rate of reaction. So how does reaction rate equation and reaction mechanism relate to one another? So we know that what is the reaction mechanism? The reaction mechanism is a series of steps, right? Describing how a reaction proceeds. So the slow step is a step that determines the reaction mechanism. So say for this equation, for these two steps in a certain reaction, so the overall reaction will be 2A plus B gives you C plus D, right? Agreed? So but then it's split up into two separate steps in the reaction mechanism, and the second step we tell you is the slow step. The slow step means a higher activation energy. Then we say that rate is now dependent on one molecule X reacting, so X to the power of 1. But the production of 1 mole of X is dependent on 2 moles of A and 1 mole of B. And we cannot leave the expression like this, because rate equation must be defined based on the reactants, concentration of the reactants, not the concentration of an intermediate. This is an intermediate. So we express it as such. Since one molecule of X is produced from 2 molecules of A and 1 molecule of B, rate equals to K times concentration of A squared times concentration of B. So another common question is that they give you some experimental data, and then you use this experiment data to calculate the rate equation. Then they give you two different mechanisms. Okay, the first mechanism maybe is A plus 2B gives you C, C gives you D plus E, and then the slow step is the first step, and then the mechanism 2. Okay, I just do a very simple illustration. Okay, 2A plus B gives you F, F gives you G, No, normally it's the same products, D plus E. And then they tell you that this is the slow step. So what do we observe? We actually observe that mechanism 1 is more likely to be the correct mechanism. Why? Because the rate equation that we deduce from this mechanism 1 will be rate equals to K times A times B squared, which is equivalent to the observed rate equation for experimental result. Whereas the rate equation that we expect from mechanism 2 will be rate equals to K times A squared times B, which would not be what we would expect from the experimental data. Okay, so that roughly wraps up my introduction into the concepts of reaction kinetics. However, to know how to apply these concepts, because remember in my first video I said there's two kinds of understanding: conceptual understanding and applicational understanding. So you have to go and try out practice questions, and I'll go through a few example questions maybe in my next video. I also did not cover the following topics, which is the following points in reaction kinetics, because those are, in my opinion, less important. The first is how to plan kinetics experiment. The second is the characteristic kinetics graphs. Okay, this is actually fairly important, but I didn't go through for lack of time. And the third is how the homogeneous and heterogeneous catalysts work. So go and revise those three on your own. I think they are fairly manageable, right? The second point is just maths, right? Knowing how to manipulate the mathematical equations. And okay, I'm done now, and see you for our next video.